Have you ever wondered what happens to the fundamental building blocks of matter when a massive object finally ceases to exist? We often think of destruction as a complete ending, but in the vast economy of the universe, nothing is ever truly wasted. An atom released from a dying star does not simply vanish. Instead, it embarks on a long, drifting migration, waiting to become part of a new structure. It is a continuous, silent cycle of recycling that operates on a scale difficult to comprehend. Exploring these quiet mechanisms is the purpose of Fall Asleep with Science. If this steady pace of discovery suits you, a gentle like and subscribe helps others find us. Now, relax, and let's follow the invisible journey of the atom. Consider the concept of permanence. We often view the physical world, people, stars, entire civilizations as solid and enduring. However, on the fundamental level, nothing is truly static. The atoms that construct reality are often described as the unbreakable building blocks of the universe, the foundational pieces from which all matter is assembled. Yet, under specific extremes, even atoms are subject to change. They can decay, they can break apart. In certain circumstances, they can vanish entirely, transforming into something different. To understand the death of matter, we must first understand how it is built. At the core of every object we can touch or see lies the atom. From the air in the atmosphere to the distant stars, all matter consists of these microscopic structures. While they appear simple from a distance, atoms are incredibly organized systems containing their own internal architecture. The center of this system is the nucleus. This dense core contains nearly all of the atom's mass. Inside the nucleus, there are two primary types of particles: protons and neutrons. Protons carry a positive electrical charge, while neutrons, as their name suggests, are neutral. They carry no charge at all. These particles are packed into an extremely small space. In normal circumstances, two positive charges would repel each other, pushing apart with significant force. However, inside the nucleus, they remain bound together. They are held in place by the strong nuclear force. This is one of the four fundamental forces of nature. Without it, the nucleus would instantly disintegrate. Surrounding this dense, heavy core is a vast region of space inhabited by electrons. Electrons are far lighter than protons or neutrons and carry a negative electrical charge. Electrons do not sit still. They exist in a cloud of constant motion, orbiting the nucleus in specific regions known as shells or energy levels. These shells are arranged at different distances from the center. The shells closest to the nucleus hold electrons with the least amount of energy, while those further out hold electrons with higher energy. Despite their speed, electrons stay within these regions because they are attracted to the positive charge of the protons in the center. This is the fundamental rule of electromagnetism. Opposites attract. This pull between the negative electrons and the positive nucleus prevents the atom from flying apart. The identity of an atom, what element it actually is determined strictly by the number of protons in the nucleus. This is called the atomic number. Hydrogen has 1 proton, helium has 2, carbon has 6. This count gives the element its name and its properties. However, an atom is also a system of balance. For an atom to be electrically neutral, it must have an equal number of protons and electrons. When these numbers match, the positive and negative charges cancel each other out. While protons define identity, neutrons define stability. Neutrons add mass to the atom and act as a buffer within the nucleus. helping to offset the repulsive forces between protons. Without neutrons, the nucleus would be unable to hold itself together. Interestingly, this balance is not always uniform. Atoms of the same element can hold different numbers of neutrons. These variations are called isotopes. For instance, a carbon atom will always have 6 protons, but it might have 6, 7, or even 8 neutrons. Some of these isotopes are perfectly stable and can last essentially forever. Others are unstable. Over time, an unstable isotope will break down in an attempt to reach a balanced state. This breakdown is the process of radioactive decay. While the nucleus handles the atom's mass and identity, the electrons determine how the atom interacts with the world. The electrons in the outermost shell are the ones that make contact with other atoms. When atoms come near each other, these outer shells can overlap, allowing electrons to be shared or exchanged. This interaction forms chemical bonds, which allow atoms to combine into molecules and complex matter. Crucially, electrons do not crash into the nucleus, despite the strong attraction pulling them inward. They possess energy from their motion, which acts as a counterforce. It is a continuous tug of war. The electric force pulls the electron in, while its motion keeps it moving forward. The result is a stable orbit. The atom, therefore, is not a solid, static marble. It is a dynamic system of tension and movement, maintaining a precise balance to exist. Each component has a specific job. Protons provide the charge and identity. Neutrons provide the mass and nuclear glue. Electrons provide the flexibility to connect and build. When these forces are in equilibrium, the atom is stable. It can form the structure of a grain of sand or a mountain range. However, if the balance shifts, if there are too many protons, too few neutrons, or an excess of energy, the system becomes unstable. While most atoms in the universe are stable, those that are not reveal a deeper connection between the material world and energy. This brings us to the concept of mass-energy equivalence. In our daily experience, mass and energy appear to be distinct. Mass is weight and substance. Energy is light, heat, and movement. In the atomic world, however, they are deeply connected. This relationship is defined by Albert Einstein's famous equation, E equals mc squared. In this equation, E stands for energy, m stands for mass, and c stands for the speed of light in a vacuum. The speed of light is a massive number, approximately 300,000 kilometers per second. When you square that number multiplying it by itself, the result is enormous. This equation tells us that a very small amount of mass equates to a huge amount of energy. In stable atoms, this relationship is quiet, but when an atom changes, the relationship becomes active. If an atom splits or transforms, a tiny fraction of its mass may disappear. This mass is not lost. It is converted directly into energy. The transformation follows the strict math of Einstein's equation. The energy produced matches the mass lost exactly. This energy can manifest as heat, light, or radiation. This is the mechanism behind radioactive decay. It is not magic. It is simply a conversion of state. When a radioactive atom decays, it often turns into a different element entirely. This is called nuclear decay. The nucleus might eject a proton or neutron, or it might split. The new atom will have slightly less mass than the original, and that missing mass accounts for the energy released. This process is not destruction, but transformation. A clear example is nuclear fission, where a large atom, such as uranium-235, splits into two smaller atoms. the process rearranges the structure of the nucleus. A small fraction of the original mass is converted into energy, which, because of the massive multiplier of the speed of light squared, results in a tremendous release of power. This principle drives nuclear reactors. The reverse process is also possible. Under extreme conditions, energy can be converted into mass. In the high-energy environment of the early universe, or in modern particle accelerators, pure energy can form particles of matter. This suggests that matter is essentially a condensed form of energy. Even within a stable, quiet atom, mass and energy are tied together. The strong nuclear force that binds the nucleus requires energy to work. This is known as binding energy. If you were to weigh a nucleus, you would find it weighs slightly less than the sum of its individual protons and neutrons. The missing mass has been converted into the binding energy that holds the nucleus together. This balance powers the stars. In the core of a star like our sun, hydrogen atoms are crushed together to form helium. This fusion process converts a small amount of mass into energy, which radiates out as sunlight. This concept also explains stability. A tightly bound nucleus has more binding energy, meaning more of its mass is dedicated to holding the system together. Less tightly bound atoms have more available mass and are more likely to decay. In every case, the total amount of mass and energy remains constant. It simply shifts forms. This is the law of conservation. Radioactive decay is the process by which unstable atoms seek this balance. There are several types of decay, each changing the atom in a specific way. One common form is alpha decay. In this process, the nucleus ejects a package called an alpha particle. An alpha particle consists of 2 protons and 2 neutrons, which is identical to the nucleus of a helium atom. Because the atom loses 2 protons, its identity changes. It shifts 2 spots back on the periodic table. For example, when uranium-238 undergoes alpha decay, it loses an alpha particle and transforms into thorium-234. This ejection process significantly reduces the mass of the atom because 4 heavy particles have departed from the nucleus entirely. The energy released during this separation is relatively high, yet, physically, alpha particles are bulky and slow. They do not travel very far. In fact, a simple sheet of paper or even the outer layer of human skin is enough to stop them cold. However, this lack of penetrating power does not make them harmless. If an alpha-emitting source is inhaled or ingested, placing it inside the body where there is no protective skin, it can cause significant damage to internal tissues. Another common method of transformation is beta decay. This occurs when the balance within the nucleus shifts in a different way. A neutron spontaneously transforms into a proton. To maintain the balance of charge and energy, the atom ejects a beta particle, which is essentially an electron, along with a tiny, ghost-like particle called an antineutrino. Because the nucleus now has 1 extra proton, the atom's identity changes. It moves 1 step higher on the periodic table. A classic example is carbon-14. When it undergoes beta decay, it transforms into nitrogen-14. This shift helps an unstable arrangement of particles move closer to a stable configuration. There is a mirror image to this process known as beta plus decay, or positron emission. In this scenario, a proton inside the nucleus turns into a neutron. The atom then releases a positron, a particle that is the antimatter counterpart to the electron, carrying a positive charge and a neutrino. Because a proton has been lost, the element shifts 1 place lower on the periodic table, This type of decay is frequently found in atoms that are proton-rich, meaning they have too many protons relative to neutrons. The life of the ejected positron is incredibly short. Almost immediately, it encounters a standard electron in the surrounding environment. When matter meets antimatter, they annihilate each other, releasing a burst of energy in the form of gamma rays. This specific reaction is the foundation of medical imaging technologies like PET scans, where positrons are used to create detailed maps of the human body. Then, there is gamma decay. Unlike the previous types, this process does not change the number of protons or neutrons. The element remains the same. Instead, gamma decay is the nucleus releasing built-up tension. After a violent event like a nuclear reaction or a previous decay, the nucleus may be left in an excited state, similar to a stretched spring vibrating with excess energy. Gamma decay is the act of letting that spring go. The energy is released as high-energy electromagnetic radiation known as gamma rays. These rays have no mass and no electrical charge, but they carry immense power. Unlike alpha particles, gamma rays can pass easily through many materials, including the human body. This penetrating ability makes them dangerous, requiring dense barriers like thick lead shielding to block them effectively. Sometimes, an atom changes not by pushing a particle out, but by pulling one in. This is called electron capture. An electron from the innermost shell falls into the nucleus and merges with a proton. Together, they form a neutron. The result is chemically the same as beta plus decay. The atomic number drops by 1. Electron capture typically occurs in atoms that have an abundance of protons, where becoming more neutron-rich allows the nucleus to settle into a more stable state. This rearrangement often causes the atom to emit X-rays as the remaining electrons shuffle down to fill the vacancy left by the captured electron. In very heavy elements, such as uranium or californium, there exists a much more dramatic process called spontaneous fission. Here, the nucleus does not just chip off a piece, it splits roughly in half. The nucleus divides into 2 or more smaller nuclei, releasing several stray neutrons and a massive amount of energy. Unlike the induced fission used in nuclear power plants, which requires a trigger, spontaneous fission happens entirely on its own. It is a rare event, but when it occurs, the atom is completely rewritten, leaving behind entirely new elements and a burst of energetic particles. The neutrons released in this split can sometimes strike nearby atoms, potentially starting a chain reaction if the conditions are right. Beyond these standard forms, there are more exotic types of decay. One example is cluster decay. In this process, the nucleus emits a small clump of particles that is heavier than an alpha particle, but lighter than a fission fragment. For instance, a nucleus might eject a neon-20 fragment. This phenomenon is exceptionally rare and is mostly observed in very heavy, unstable elements. Even rarer is double beta decay. This happens when 2 neutrons simultaneously transform into 2 protons, releasing 2 beta particles and 2 antineutrinos. This process is agonizingly slow, taking billions of years to occur, but it happens in specific isotopes where single beta decay is energetically forbidden. A theoretical version of this, called neutrinalis double beta decay, has been proposed but not yet confirmed. If discovered, it would prove that neutrinos are their own antiparticles, unveiling a completely new layer of physics hidden within the decay process. All these transformations are driven by the complex interplay of forces inside the nucleus. The system must constantly balance the glue-like pull of the strong nuclear force against the explosive push of electromagnetic repulsion. When that balance is off, the atom will find a way to adjust. Sometimes that means shedding a particle. Other times, it means changing the identity of a proton. And sometimes, it simply means releasing pure energy. This leads us to rethink the concept of atomic longevity. When we consider something breaking down, we naturally ask, how long will it last? For radioactive atoms, the standard measure is the half-life. A half-life is the time it takes for 50% of a sample of radioactive atoms to decay into something else. It is a useful, simple number that helps us make predictions. However, it does not tell the whole story. A half-life is not a countdown clock. It is not the age at which an atom dies. Instead, it is a measure of probability. Imagine you start with a collection of 1,000 atoms of a radioactive element with a half-life of 10 years. After 10 years, approximately 500 atoms will remain. After another 10 years, about 250 will be left. But this does not mean any specific atom was destined to last 20 years. Some decay almost instantly, while others might linger for millennia. The half-life describes the average behavior of the crowd, not the destiny of the individual. When we zoom in to the level of a single atom, the idea of a lifespan becomes blurry. Decay does not follow a schedule. There is no ticking mechanism inside the nucleus counting down the seconds. Instead, each atom exists in a state where decay is merely a possibility. It is as if the atom is constantly flipping a coin in secret. Every moment carries a tiny statistical chance that the nucleus will change. When the coin finally lands the right way, the atom releases its energy and transforms. But we can never predict exactly when that moment will arrive. Some atoms, like polonium-214, flip this coin frantically. Their half-life is less than a fraction of a second. Others, like tellurium-128, have half-lives so long they are difficult to comprehend, spanning trillions of years. Yet, both are governed by the same quantum rules. The difference lies in the stability of their internal structure and the energy barrier they must overcome. A minuscule change in nuclear structure can shift the decay rate by an astronomical amount. This means two atoms that look very similar might experience time in vastly different ways. For a long time, scientists believed that half-lives were fixed constants, immune to the outside world. However, modern experiments have shown that in rare cases, external conditions can have a subtle effect. For example, stripping an atom of all its electrons or placing certain isotopes in intense environments can slightly alter how fast they decay. These changes are minute, but they suggest that half-lives are not quite as absolute as once thought. Factors like temperature, pressure, or chemical bonding usually have no impact, but under extreme astrophysical conditions, the rules can bend. There is also the phenomenon of isomers. These are atoms with the same number of protons and neutrons as a stable version, but their nucleus is stuck in a high-energy arrangement. These nuclear isomers can remain in this excited state for a surprisingly long time before finally dropping down to a lower energy state. Their half-lives can range from seconds to decades. They wait not because they are stable, but because the path to decay is blocked. It is comparable to water held back by a dam. The potential to flow is there, but the structure holds it in place. Sometimes, the push needed to break the dam doesn't come from within. A passing particle or a stray photon can trigger the release, a process known as induced decay. When we consider all these factors, the definition of an atom's life becomes elusive. It is not a timeline with a birth and a death. It is a probability held open over time. The longer an atom survives without decaying, the more statistically unlikely its survival becomes. Yet it is never impossible. This is why we can still find radioactive isotopes that were forged in the fires of the early universe. They are rare, but they are not gone. Their rate of decay is simply slow enough that they have persisted for billions of years. This reality challenges how we perceive time in the atomic realm. A half-life implies a smooth, steady fading away, but for the atom, decay is instantaneous. It happens in jumps, sudden, violent moments of change. Between those jumps, nothing happens. Time passes, but the atom remains exactly identical to how it was a billion years ago. This makes atomic aging fundamentally different from biological aging. It is not a slow wearing down of parts. It is a stillness, waiting for a single, transformative event. Some physicists have even speculated whether time itself behaves differently at these scales. In the quantum world, energy and matter are not continuous. They come in discrete packets. It is possible that the flow of time inside a nucleus is also step-like rather than smooth. It may not be enough to ask how long an atom lasts. We may need to ask how time flows within it. Ultimately, the half-life is a tool for us, not a rule for the atom. It allows us to manage nuclear waste and plan medical treatments. But in the light of physics, it is a signpost, not a boundary. This leads us to the broader principle driving these changes: entropy. We see it everywhere. Ice melts into puddles, buildings weather and crumble, heat dissipates from a warm object into cool air. These are all manifestations of a deep universal rule known as the second law of thermodynamics. It states that in any closed system, the total amount of disorder or entropy will never decrease on its own. It will either stay the same or increase. Entropy is frequently described as a measure of chaos, but it is more accurate to think of it as a measure of probability. Consider a deck of cards. A deck arranged in perfect numerical order has low entropy because there is only one way to achieve that specific sequence. A shuffled deck has high entropy because there are virtually infinite ways for the cards to be mixed up. Nature, left to itself, always drifts from the ordered stack toward the shuffle. The universe favors disorder not because it is destructive, but because disorder is statistically more likely. At the subatomic level, radioactive decay is an agent of this law. An unstable atom represents a concentrated, precise, and high-energy arrangement. Over time, it shifts toward a lower energy, more common state. The result is a transition where strict order is replaced by a wider range of possibilities. Even though the individual changes happen on a microscopic scale, the direction is always the same, toward more randomness and higher entropy. Take the example of a uranium atom. When it eventually emits an alpha particle, that act does more than just change the element. It spreads energy out into the surrounding environment and increases the number of independent particles. Where there was once a single, unified object, there are now smaller, separate pieces, each free to move in different directions. The system has gained more possible arrangements, more freedom of movement, and therefore more entropy. Even though energy is often viewed as the primary currency of atomic reactions, there is another rule that is equally powerful: entropy. A transformation might release very little energy, yet it will still occur simply because it leads to a state of greater disorder. In fact, some changes that appear energetically unfavorable can proceed if they result in a significant enough rise in entropy. It is as if the universe is willing to expend a certain amount of energy to gain more statistical possibilities. This principle explains why distinct phenomena, such as the spontaneous mixing of gases or the decay of specific isotopes, happen naturally without external force. In the microscopic realm, the increase of entropy is not always immediately obvious. Atoms do not become messy in the way a neglected room does, but the shift is real. When a particle decays, the system it was once part of becomes more complex. There are suddenly more independent pieces, more trajectories, and more ways for the matter to spread out. The total energy remains constant, but the precise order that once existed is lost. We perceive this locally as the flow of time. We watch glasses fall and shatter, but we never see shards spontaneously reassemble into a glass. Systems naturally drift toward disorder. Because this increase in entropy cannot be reversed without the input of external work, we experience time as a one-way journey from low entropy to high entropy. This rule applies to the massive scale of planets and stars, and it applies with equal rigor to the atomic nucleus. Entropy is the reason some atoms are stable while others are not. A stable atom already resides in a state of low energy and high entropy. It has little to gain by changing. An unstable atom, however one vibrating with excess energy or holding an awkward number of neutrons, exists in a state of tension. Its current form is improbable and too ordered. By decaying, the atom transitions into a form that is statistically more probable. Entropy clarifies why atomic decay is effectively irreversible. Once an atom fractures or transforms, it does not spontaneously revert to its original state. To reverse the process, one would need to force every particle back into the exact same structure, with the exact same position and energy. The level of order required is so specific and so unlikely that, for all practical purposes, it never happens. Destruction is easy. Reconstruction requires precise, deliberate intervention. Without entropy, atomic changes might appear random or wasteful. Through the lens of entropy, however, we see that each decay contributes to a universal drive. These small acts of atomic reorganization are part of the vast process that shapes the cosmos, from the burning of stars to the chemistry of life. Yet, while entropy drives the direction of change, the environment dictates the speed and intensity. In the core of our sun, temperatures soar to over 15 million degrees Celsius. The pressure is millions of times greater than the atmospheric pressure at Earth's surface. In this inferno, atoms are stripped of their electrons and squeezed together with such intensity that they begin to fuse. Hydrogen nuclei collide, combining to form helium. But fusion does not occur simply because atoms are crowded. It requires extreme heat to provide the particles with enough speed to overcome their natural repulsion. Protons are positively charged, and like charges, repel. Under normal conditions, this electromagnetic barrier keeps atoms apart, preserving their individuality. In the heart of a star, however, particles move with such velocity that they crash through this barrier. When they get close enough, the strong nuclear force, which is powerful but acts only over incredibly short distances, snaps them together. A new nucleus is forged. In this moment, a small fraction of mass is converted into a large amount of energy. In such extreme environments, decay processes that might normally take thousands or millions of years can accelerate dramatically. The intense heat and pressure shift the energy balance of the nucleus. For some isotopes, this environment makes it easier to eject particles. For others, the external pressure forces them into stability. Supernovae represent an even more violent stage for atomic change. In the final moments of a massive star's life, the delicate balance between the inward pull of gravity and the outward push of nuclear fusion collapses. The core implodes, causing pressure to spike and temperatures to skyrocket to billions of degrees. Under these cataclysmic conditions, heavy elements like gold, uranium, and plutonium are created in a matter of seconds. These atoms are not built slowly. They are hammered into existence by crushing forces that smash lighter elements together. Some of these newly formed atoms decay almost instantly, releasing waves of radiation that flood the surrounding space. Others survive, drifting through the cosmos for eons until they settle into dust clouds, eventually becoming part of new planets or living organisms. On Earth, we replicate these extreme conditions in controlled environments like nuclear reactors and particle accelerators. Inside a reactor, heavy atoms like uranium-235 are bombarded with neutrons. These extra neutrons destabilize the nucleus, increasing the probability of a split. When the nucleus fractures, it releases energy, additional neutrons, and smaller atomic fragments. These released neutrons strike other atoms, triggering a chain reaction. This self-sustaining cycle is the basis of nuclear power generation. The temperature within a reactor core can climb to thousands of degrees, and the neutron flux is kept deliberately high to ensure atoms continue to break apart. This environment alters the natural rules. Isotopes that would remain stable in the ground can become unstable under this bombardment. Those that decay slowly may be forced to disintegrate much faster. The environment effectively rewrites the timeline of decay. In particle accelerators, scientists push matter even further. They strip atoms of their electrons to create ions and accelerate them to near the speed of light. When these high-speed particles collide, the kinetic energy is sufficient to shatter nuclei or even generate entirely new particles from pure energy. Some collisions mimic the conditions of the universe just moments after the Big Bang. Others allow researchers to synthesize artificial atoms that do not exist in nature, elements so unstable they exist for only a fraction of a second. Yet, in that brief flash, they reveal the extreme limits of material existence. Deep inside massive planets like Jupiter, gravity creates pressures that squeeze atoms to an unparalleled degree. Hydrogen transitions into a metallic state, conducting electricity. Atoms are forced closer together than standard chemistry would allow, altering how electrons behave and how chemical bonds form. Some atoms may begin to decay in ways impossible in a vacuum. In plasmas, the fourth state of matter, atoms are heated until their electrons are ripped away entirely. The result is a chaotic soup of free nuclei and electrons. In this state, electrons can reattach in strange configurations, and nuclei can interact with unexpected partners. The most profound atomic transformations occur in the universe's most violent locations. In neutron stars, gravity packs matter so tightly that protons and electrons merge, crushing the atom out of existence and leaving behind a dense sea of neutrons. In black holes, matter is pulled inward with such ferocity that the known laws of physics cease to function. These are not places of stability. They are engines where atoms are stretched, torn, and reborn into forms we are only beginning to understand. This leads us to the concept of nuclear instability, the mechanics of a crumbling core. For many elements, the balance of forces within the nucleus holds firm for billions of years. For others, stability is fleeting. As atoms become larger, they require an increasing number of neutrons to maintain their structure. This is a consequence of the range of forces. The strong nuclear force acts as the glue, but it only works across very short distances. The electromagnetic force, which pushes protons apart, acts over long distances. As a nucleus grows and protons are spaced farther apart, the glue of the strong force struggles to hold the outer edges. Therefore, larger atoms need more neutrons to act as buffers and binding agents. If an atom lacks sufficient neutrons, the strong force cannot counteract the electromagnetic repulsion. The protons push away from each other, rendering the nucleus unstable. A key indicator of an atom's health is the proton-to-neutron ratio. In light elements, stability is found in a 1-to-1 balance. However, in heavy elements like uranium or thorium, the number of neutrons must significantly outnumber the protons. If the ratio is off, too many protons or too few neutrons, the nucleus will decay. Another factor is the energy state. Every nucleus contains a specific amount of stored energy. The arrangement of protons and neutrons dictates how much energy is required to keep the system bound. If a nucleus is in a high energy state, it naturally seeks a lower energy configuration, often achieving this through radioactive decay. For some elements, instability arises from an excess of neutrons. The strong nuclear force can only contain so much. Eventually, the nucleus reaches a saturation point. The extra neutrons create an imbalance, prompting the atom to emit alpha or beta particles to shed mass and energy. This is the atom's attempt to slim down to a stable size. Conversely, in isotopes like certain forms of iodine or carbon, the instability comes from having too many protons. The repulsion between the positive charges overwhelms the binding force, causing the nucleus to fracture. This typically results in beta decay. While the strong nuclear force fights to hold the core together, the electromagnetic force works to tear it apart. When these forces lose their equilibrium, stability is lost. The nucleus breaks down, transforming into a different element and releasing radiation. This energy release is why radioactive materials pose a danger to biological life. The atom is physically ejecting parts of itself to survive. However, the behavior of these particles is not always straightforward. This brings us to a phenomenon that defies classical logic: quantum tunneling. In the everyday world, objects follow clear rules. If you throw a ball at a solid wall, it will bounce back. It cannot pass through unless it has enough energy to break the wall. In the subatomic world, however, particles behave in ways that seem impossible. Quantum tunneling describes how a particle can pass through a barrier that, according to classical physics, it should not be able to cross. Imagine a proton trapped inside a nucleus, held in by the strong nuclear force. This force acts as a barrier. Classical physics dictates that unless the proton has enough energy to climb over that barrier, it must stay inside forever. But in the quantum realm, a particle is not a solid, defined object with a single location. Instead, it exists as a wave function, a cloud of probabilities. This wave function defines where the particle might be. Most of the probability is centered inside the nucleus, but the wave does not stop abruptly at the wall. It tails off, extending slightly into and even through the barrier. This means there is a small, but non-zero, probability that the particle is actually on the outside. Because of this wave-like nature, a particle does not need to break the wall. It does not need to climb over it. Occasionally, the probability wave collapses, and the particle simply appears on the other side. It is tunneled through the energy barrier without having the energy to beat it. This implies that even if a particle is trapped, it is never truly 100% contained. There is always a statistical chance, however minute, that it can appear elsewhere. This strange ability to bypass barriers is the essence of quantum tunneling. One of the most profound examples of this quantum rule breaking occurs during alpha decay. Picture the nucleus as a fortress. Inside, an alpha particle is trying to leave. However, it is trapped behind a massive energy wall created by the strong nuclear force and the electrostatic repulsion between the positively charged particle and the rest of the nucleus. According to the strict laws of classical physics, this escape should be impossible. The alpha particle simply does not possess enough energy to climb over the wall. It should be trapped inside forever. Yet, in the quantum world, the rules are different. As the alpha particle approaches the barrier, it does not need to summon the energy to jump over it. Instead, it borrows energy from the quantum system itself, allowing it to slip through the wall as if it were a phantom. It does not climb, it tunnels. One moment it is inside, and the next it appears on the outside. This process allows the atom to decay even though it lacks the raw power to surmount the forces holding it together. The likelihood of this happening depends heavily on the architecture of the barrier. If the energy wall is too thick or too high, the tunnel is hard to dig, and decay becomes rare. This is why some isotopes remain stable for eons. However, if the barrier is thin enough, the particle's wave function, its cloud of probability, extends easily to the other side, making decay almost inevitable. This same ghostly mechanism is the engine of the stars. In the core of our sun, hydrogen nuclei are moving at incredible speeds, heated to millions of degrees. Yet, even this extreme heat is not enough to overcome the electromagnetic repulsion that pushes protons apart. Classical physics suggests the sun should not shine. The protons should simply bounce off one another. But thanks to quantum tunneling, they can cheat the system. They tunnel through the repulsion barrier to fuse together, creating helium and releasing the sunlight that sustains life on Earth. Without this quantum shortcut, the universe would be a much darker place. This phenomenon is not limited to the cosmos. It governs the technology in our pockets. The flow of electrons in semiconductors, transistors, and modern microchips relies on tunneling. It is also the foundation of future technologies like quantum computers. But while tunneling allows atoms to change quietly, other transformations are far more violent. Consider the fate of an atom in a high-energy collision. When two particles act as projectiles, smashing into each other at speeds approaching the speed of light, the energy involved is catastrophic. In these extreme conditions, the forces that bind protons and neutrons are pushed past their breaking point. This leads to nuclear fragmentation. In massive particle accelerators, we accelerate atoms to such velocities that their kinetic energy overwhelms the strong nuclear force. Upon impact, the nucleus does not just split, it shatters. The outcome depends on the angle and energy of the crash. Often, the result is a spray of new particles and the birth of entirely new atoms. At the highest energy levels, the nucleus undergoes multifragmentation, exploding into a debris field of smaller nuclei, mesons, and other subatomic particles that are rarely seen in stable matter. These collisions are a window into the fundamental architecture of reality. By smashing atoms apart, researchers can synthesize heavy elements that do not exist naturally on Earth, members of the so-called island of stability. These synthetic atoms are often incredibly unstable, existing for mere fractions of a second. Yet they help us map the outer limits of the periodic table. In the most extreme cases, the collision energy is so intense that it dissolves the protons and neutrons themselves. The atom is stripped down to its most basic components, quarks and gluons. This recreates the state of the universe just moments after the Big Bang. This primordial soup, known as a quark-gluon plasma, is a state of matter that existed before the first atomic nucleus was ever formed. Facilities like the Large Hadron Collider allow us to step back in time, observing these conditions to solve mysteries like the nature of dark matter. But destruction is only half the story. When an atom decays or is destroyed, the energy must go somewhere. This is the process of energy redistribution. It is not just about the breakdown of matter. It is about the flow of heat, light, and motion into the universe. When an atom undergoes alpha or beta decay, the ejected particles carry kinetic energy away from the scene. Often, the atom is left in an agitated state and must release excess energy as electromagnetic radiation, specifically gamma rays. These high-frequency waves act as carriers, transporting energy across vast distances. When this radiation encounters other materials, it transfers that energy, causing heating or ionization. On a planetary scale, this microscopic process drives geology. The Earth's crust is rich in radioactive isotopes like uranium and thorium. As they slowly decay, they release heat. This ancient atomic heat keeps the Earth's core molten, driving the movement of tectonic plates, fueling volcanoes, and shaping the continents. Without the death of these atoms, our planet would be geologically dead. We also harness this redistribution for human needs. In a nuclear power plant, the energy released from fission is captured by a coolant used to boil water and turned into steam to drive turbines. It is a controlled harvest of atomic energy. In medicine, we use it to heal. Radioactive isotopes are used in radiotherapy, where high-energy radiation is focused precisely on tumors. The energy from the decay damages the DNA of cancer cells, halting their growth while sparing healthy tissue. In diagnostic imaging, like PET scans, the energy released helps us map the internal structures of the living body. However, this energy is a double-edged sword. In uncontrolled environments, high doses of radiation damage living tissue, causing burns, genetic mutations, or death. It can create free radicals, highly reactive chemical species that tear apart cells. This is why the handling of radioactive materials requires such stringent safety protocols. Ultimately, this flow of energy follows the laws of thermodynamics. Energy moves from concentration to dissipation, increasing the entropy of the universe. The potential energy locked inside a nucleus is freed, becoming heat or light, spreading out into the void. This leads us to consider the concept of atomic phase transitions. We are familiar with the idea of phases in water freezing into ice or boiling into steam. Atomic systems also undergo phase transitions, though they are often more subtle. These are shifts in the internal structure or behavior of the atom under different conditions. A common example is an electronic transition. When an atom absorbs energy, an electron can jump from a low-energy orbit to a higher one. This is the atomic equivalent of a solid melting. The atom moves from a stable ground state to an excited state. When the electron falls back down, it releases that energy as light. This is the mechanism behind neon signs and lasers. More drastic transitions involve the nucleus itself. Nuclear fission can be seen as a phase transition, where a single large nucleus splits into two smaller ones, similar to a material fracturing under stress. Conversely, fusion is a transition where distinct particles merge into a unified whole. There are also transitions that affect how atoms interact with one another. In certain materials, Cooling them to extremely low temperatures causes a shift in the electron cloud, leading to superconductivity. In this state, electrical resistance disappears entirely, and the material behaves in a fundamentally different way. These transitions, sometimes occurring at quantum critical points, show us that atoms are not static bricks. They are dynamic entities that change their nature depending on their environment. But of all the environments in the universe, none are as hostile or as transformative as the gravitational maelstrom. The powerful gravitational fields near massive celestial objects have a profound effect not only on the orbits of stars and planets, but on the very atoms that construct them. The influence of gravity, particularly near black holes, introduces a new dimension to our understanding of atomic behavior. Black holes are regions in space where mass is packed so densely and gravity pulls so strongly that not even light can escape. They represent the ultimate distortion of space-time, a cosmic trap where the rules of existence are rewritten. These objects are not merely heavy. They are regions where mass has collapsed to such density that gravity overwhelms all other forces. Surrounding them is the event horizon, a boundary often described as the point of no return. Beyond this invisible line, the escape velocity exceeds the speed of light, since nothing can travel faster than light. Nothing, not a photon, not a signal, not an atom, can ever report back on what lies inside. This extreme environment exerts immense forces on any matter that ventures too close, causing time to stretch and space to bend in ways that defy our intuitive understanding of reality. One of the most striking and disorienting consequences of existence near a black hole is the warping of time itself. We tend to think of time as a constant, a steady drumbeat that plays at the same tempo for everyone, everywhere. But relativity teaches us that time is flexible. It is a dimension that can be stretched by gravity. As an object approaches the event horizon, time appears to slow down relative to an observer watching safely from a distance. This phenomenon, known as time dilation, occurs because gravity effectively drags the fabric of space-time, slowing the clock's rhythm. Imagine an atom of a radioactive element drifting toward this abyss. For the atom itself, nothing feels different. Its internal processes continue as normal. However, for a telescope watching from Earth, the picture is radically different. As the atom gets closer to the black hole, its movements appear to become sluggish. The light it emits shifts toward the red end of the spectrum, losing energy as it climbs out of the gravitational well. Crucially, its decay process, the very act of dying, appears to pause. An unstable isotope that should decay in minutes might appear to linger for centuries from our perspective, frozen in a state of suspended animation just above the horizon. Yet, if you were falling alongside that atom, glancing at your own watch, the decay would happen right on schedule. You would look back at the universe you left behind and see events there unfolding at a frantic pace, as if someone had hit the fast-forward button on cosmic history. These conflicting realities exist simultaneously, separated only by the warping of gravity. It forces us to ask, when does the atom actually die? The answer depends entirely on where you are standing when you ask the question. But gravity near a black hole does more than just play tricks with time. It physically assaults the atomic structure. As an atom falls closer, it experiences tidal forces. These forces arise because gravity's pull becomes significantly stronger over very short distances. The side of the atom closer to the black hole is pulled much harder than the side facing away. In deep space, this difference is negligible, but near a singularity, The gradient is steep enough to overcome the forces holding the atom together. This leads to a process with a grimly whimsical name: spaghettification. The atom is stretched vertically and compressed horizontally. The tidal forces disrupt the delicate balance of the nucleus. The electromagnetic bonds holding electrons in orbit are overwhelmed, ripping them away. Even the nucleus itself, the fortress of the atom, begins to buckle. The protons and neutrons are pulled apart, forcing the atom to undergo a type of decay driven not by the random roll of quantum dice, but by the sheer, crushing, brute force of gravity. In this final descent, the atom is not just decayed, it is dismantled, shredded into its elementary components before vanishing into the dark. When atoms are subjected to such violence, whether by the crushing grip of gravity, the intense heat of a star, or the shockwave of an explosion, they often enter a new state of existence. This is the realm of plasma. To understand plasma, consider the transformation of water. If you heat a block of ice, the rigid crystal lattice breaks and it melts into liquid water. If you heat the water, the molecules break free of each other, boiling into steam. But what happens if you continue to heat the steam? If you push the temperature to thousands or even millions of degrees, the energy becomes too great for the atoms to hold themselves together. The kinetic energy of the electrons becomes so intense that they are ripped from their orbits. They can no longer remain bound to the nucleus. This moment marks the birth of plasma. The neatly organized structure of the neutral atom, a central nucleus surrounded by a polite cloud of electrons, is obliterated. In its place is a chaotic, electrifying soup of positively charged ions and free-roaming electrons, all moving at breakneck speeds. This is not merely a hot gas. It is a fundamentally different state of matter with unique properties. Because the electrons are stripped free, plasma is electrically conductive. It responds to magnetic fields, twisting and turning in complex ribbons of energy. It glows with the light of de-excitation as particles crash into one another. In fact, if you look at the universe as a whole, the solid, liquid, and gas states we are familiar with on Earth are the exception. The universe is 99% plasma. Our own sun is a giant, roaring sphere of it. In the solar core, temperatures reach 15 million degrees Celsius. Here, the plasma is so dense that it creates the conditions for thermonuclear fusion. In a normal gas, atoms bounce off each other like bumper cars. But in the solar plasma, the nuclei are stripped bare and squeezed together until they fuse, transforming hydrogen into helium and releasing the energy that lights our solar system. Without the plasma state, the stars would not shine, and the universe would be a cold, dark void. Plasma is also the child of catastrophe. When a massive star reaches the end of its life and detonates in a supernova, the explosion generates a shockwave of superheated plasma that tears through space at thousands of kilometers per second. This expanding cloud of ionized gas, often visible to us as a nebula, becomes the nursery for future generations of stars. The heavy elements forged in the explosion are carried on these winds of plasma, eventually cooling to form planets and, ultimately, us. On Earth, we witness the power of plasma in the fleeting violence of a lightning bolt. When an electrical charge builds up in storm clouds, the voltage difference between the cloud and the ground becomes immense. Eventually, the air itself, normally an insulator, breaks down. The electrical stress rips electrons from air molecules, creating a narrow channel of plasma. This conductive path allows the massive electrical discharge to strike the ground. The air in this channel is superheated to 30,000 degrees Celsius, 5 times hotter than the surface of the sun, in a fraction of a second. The The sudden expansion of this superheated air creates the shock wave we hear as thunder. Scientists are now trying to harness this fourth state of matter to build the ultimate power source, fusion reactors. In machines like tokamaks, powerful magnetic fields are used to trap and control a donut-shaped ring of superheated plasma, attempting to replicate the conditions of the sun inside a laboratory. The challenge is immense because plasma is unruly and unstable, constantly trying to escape the magnetic cage. But if successful, it would provide humanity with a nearly limitless source of clean energy, fueled by the same physics that powers the stars. But even as we look at these large-scale states of matter, we must return to the fundamental nature of the particles themselves. When an atom decays and spits out debris, an alpha particle, a beta particle, or a gamma ray, what exactly is that debris? Is it a solid bullet, a tiny distinct object, or is it a ripple, a disturbance in a field? The answer, unsettlingly, is that it is both at the same time. This is the concept of wave-particle duality, and it sits at the heart of the quantum mystery. To understand it, we must look at light. For centuries, scientists debated whether light was a wave, like sound, or a stream of particles, like rain. It turns out, it is both. Light travels through space like a wave, bending around corners and interfering with itself. But when it hits a metal surface, it strikes like a particle, knocking electrons loose in a phenomenon called the photoelectric effect. This same duality applies to the fragments of a dying atom. Take an alpha particle. In our mental model, we picture it as a tiny, solid clump consisting of 2 protons and 2 neutrons, a microscopic cannonball. But in the quantum view, it is also a wave. Its position is not a fixed point in space, but a spread-out cloud of probability. When it travels through matter, it can diffract, bending its path as it passes through the gaps between atoms, just like a water wave bending around a rock. Gamma rays show this duality even more clearly. They travel across the galaxy as waves of electromagnetic energy, shifting and stretching. Yet, when they encounter a cell in the human body or a detector in a lab, they deliver their energy in a discrete, concentrated packet, acting indistinguishably from a particle collision. Everything in the quantum world is described by a wave function, a complex mathematical code that tells us where a particle might be, rather than where it is. Until we measure it, the particle exists in a haze of possibility. It is everywhere and nowhere at once. When an unstable atom decays, the exact moment it happens and the specific direction the particle flies are determined by this wave function. It is not a clockwork mechanism. It is a game of chance. This leads to profound philosophical questions about the nature of reality. When a particle is emitted, does it have a defined path, or does it exist as a spreading sphere of potential until it hits something? Experiments suggest the latter. The particle seems to explore every possible path simultaneously, only choosing a definite location when it interacts with the environment. This means that the debris of atomic death is not just matter, it is information, encoding the probabilities of the universe. In our detectors, whether they are Geiger counters, cloud chambers, or modern semiconductors, we force these waves to collapse. We hear the sharp click of the machine, confirming that the wave has become a particle. We see the vapor trail in the chamber, marking a definite path. But before that measurement, the particle was a ghost, a wave of potential rippling through the dark. But the quantum world gets stranger still. If we zoom in on the empty space through which these particles travel, we find that it is not empty at all. Imagine a perfect vacuum, a sealed box with absolutely nothing inside. No air, no atoms, no light, no radiation. In classical physics, this is a void, a region of absolute stillness. In quantum physics, however, this void is a hive of frantic activity. The vacuum is teeming with what we call virtual particles. These are ghost-like entities that pop into existence for a fleeting fraction of a second, borrowing energy from the vacuum itself before vanishing back into nothingness. They appear in pairs, a particle and its antiparticle flashing into existence and then annihilating each other almost instantly. They are called virtual because they do not stick around long enough to be captured directly by our instruments. They cheat the laws of conservation of energy by existing for such a short time that the universe effectively doesn't notice the dead. Think of the vacuum not as an empty stage, but as a vibrating, frothy ocean. These virtual particles are like the foam that bubbles up and dissolves on the surface. They create a background hum, a texture to space itself, and crucially, they affect the behavior of real, permanent matter. An electron traveling through space is never truly alone. It is surrounded by a cloud of these virtual particles, which buzz around it like flies, slightly altering its mass and its charge. This vacuum polarization is a measurable effect. We have experimentally confirmed that the empty space modifies the properties of atoms. In the process of radioactive decay, these virtual particles play a critical role as messengers and lenders. Consider beta decay, where a neutron inside a nucleus transforms into a proton. This change requires the mediation of the weak nuclear force. The carriers of this force are the W and Z bosons. These are massive particles dozens of times heavier than the proton itself. Here is the puzzle. The neutron does not have enough energy to create a massive W boson. It is like a person with $10 trying to buy a Ferrari. Yet, the decay happens. How? The answer lies in the quantum lone system. The W boson appears as a virtual particle. It borrows a massive amount of energy from the vacuum, performs the transformation, and then vanishes before the deadline set by the Heisenberg uncertainty principle. Without this ability to borrow energy and existence from the vacuum, the weak nuclear force could not function. The sun would not be able to fuse hydrogen. Radioactive decay would cease. The universe would be static and dead. These virtual particles, emerging from the nothingness, are the invisible bridge that allows matter to transform. They are the silent facilitators of atomic death and rebirth, proving that in the quantum realm, even emptiness is alive with potential. One of the most striking proofs that the vacuum is not empty comes from a phenomenon known as the Casimir effect. Imagine placing two uncharged metal plates in a vacuum, parallel to each other and incredibly close together, separated by a distance of only a few nanometers. According to classical physics, absolutely nothing should happen. There is no electrical charge to pull them together, no air pressure to push them. They should hang there, suspended in nothingness. But in the real world, they don't. They are pushed together by a mysterious force. This happens because the vacuum outside the plates is teeming with virtual particles of all wavelengths, long, short, and everything in between. However, the narrow gap between the plates restricts the type of virtual particles that can pop into existence there. Only particles with very short wavelengths can fit in that tight space. This creates an imbalance. There are more virtual particles pushing on the outside of the plates than there are pushing from the inside. The result is a net pressure that forces the plates together. This effect, while incredibly subtle, demonstrates a profound truth. The nothingness of empty space has weight and substance. It proves that virtual particles are not just mathematical ghosts, they are physical drivers of reality. In fact, these fleeting entities are what allow the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force to operate at all. Without these brief disturbances in the quantum field, atoms would not hold together, and radioactive decay would not occur. They are the hidden gears of the universe, shaping the outcome of atomic processes while remaining just out of reach of direct observation. But if virtual particles are the ghosts of the quantum world, then quantum entanglement is its telepathy. Albert Einstein famously dismissed entanglement as spooky action at a distance. He struggled to accept the idea that two particles could be linked in such a way that the fate of one is instantly tied to the fate of the other, regardless of how far apart they are. Yet, experiment after experiment has proven him wrong. Entanglement is real, and it plays a critical role in the death of atoms. When an unstable atom decays, the particles it ejects do not simply fly off as independent, isolated bullets. They are often born entangled. This means their quantum states are fundamentally linked. They are not two separate objects. They are a single system, stretched across space. Consider a particle with zero spin that decays into two smaller particles. Conservation laws dictate that the total spin must remain zero. If one particle spins up, the other must spin down. But here is the catch. Until you measure them, neither particle has a defined spin. They both exist in a superposition of spinning up and down simultaneously. They are undefined. Now, imagine these two particles fly apart. One travels to a detector in a lab on Earth. The other travels to a detector on Mars. For minutes, hours, or even years, they remain in this undefined state. But the moment you measure the particle on Earth and find it spinning up, the particle on Mars, instantly faster than the speed of light, snaps into the down state. It does not matter if they are separated by a room or a galaxy. The connection is instantaneous. This phenomenon, known as non-locality, shatters our classical understanding of space. It implies that, at a fundamental level, distance is an illusion. The two particles are still touching, still part of the same whole, connected by a quantum thread that ignores the limits of geography. The decay of an atom, therefore, is not just a localized event. It creates a web of connections. A single radioactive atom might emit multiple photons or particles in a cascade, all entangled with one another. As these particles spread out, interacting with other atoms, the web grows. In theory, every decay event sends ripples of information across the quantum field, linking systems that appear completely separate. This leads us to a fascinating possibility. If particles remain connected after separation, does the dead atom ever truly leave? Its debris carries the information of its past. The spin, the energy, the momentum, all are conserved and transmitted to the new particles. The entanglement ensures that the history of the parent atom is not erased, but rather distributed. The atom has not vanished. It has been disassembled and scattered, yet the pieces remain in constant, instant communication. This forces us to rethink the very concept of death in a quantum world. In our biological experience, death is final. An organism stops functioning, a machine breaks, a fire burns out. We are accustomed to endings. But in quantum mechanics, The concept of a full stop does not exist. The equations of quantum physics are unitary, which is a fancy way of saying that information is never lost. The past determines the future, and if you knew the complete quantum state of the universe today, you could theoretically reconstruct its state yesterday. When we say an atom dies through decay, we are using a human metaphor for a physical transition. The atom changes its identity. Uranium becomes thorium, carbon becomes nitrogen, but nothing is actually destroyed. The wave function, which describes the probability of the atom's existence, does not simply blink out. It evolves, it spreads, it changes shape. This idea becomes even more complex when we consider superposition. Before an atom decays, it exists in a state of being both intact and decayed at the same time. It is only when it interacts with the environment, when the Geiger counter clicks, that the universe is forced to choose one reality. This is the heart of the famous Schrödinger's cat thought experiment. A cat is placed in a sealed box with a vial of poison rigged to a radioactive atom. If the atom decays, the poison is released and the cat dies. If the atom does not decay, the cat lives. Quantum mechanics tells us that until we open the box, the atom is both decayed and not decayed. Therefore, the cat is both dead and alive. While this scenario is meant to highlight the absurdity of applying quantum rules to everyday objects, it raises a serious question. Is death an objective reality, or is it a product of observation? Does the atom truly decay if no one is watching? In the quantum view, reality is not a fixed script. It is an unfolding process of interaction. Furthermore, we must consider the Heisenberg uncertainty principle. This rule states that there is a fundamental limit to how precisely we can know the properties of a particle. We cannot know its position and its momentum with perfect accuracy at the same time. This fuzziness is built into the fabric of nature. It means that we can never define the exact moment of an atom's death with infinite precision. There is no sharp line where existence ends and non-existence begins. There is only a shifting gradient of probabilities. Even in the most extreme cosmic graveyards, black holes, the question of death is debated. For decades, physicists worried about the information paradox. If matter falls into a black hole and the black hole eventually evaporates via Hawking radiation, does the information contained in that matter disappear forever? If so, it would violate the fundamental laws of quantum mechanics. Recent theories suggest that the information is preserved, perhaps encoded on the surface of the black hole like a hologram, or released in subtle correlations in the radiation. If this is true, then even being crushed into a singularity is not a true end. The information that made you, or made an atom, persists in the scrambling of the universe. So, rather than speaking of death, we should speak of redistribution. In a world where energy is conserved and information is preserved, nothing ever truly ends. It simply changes form. The particles that make up a dying star will eventually become the carbon in your DNA. The energy released by a decaying atom will become heat, then light, then motion. The universe is a closed system of constant recycling. However, there is one process that comes closer to true death than any other. It is the violent meeting of opposites, annihilation. This occurs when matter meets antimatter. For every fundamental particle in the universe, there exists a mirror image, an antiparticle. The electron has the positron, the proton has the antiproton. These antiparticles are nearly identical to their normal counterparts. They have the same mass, the same spin, the same lifetime, but they have opposite, electrical charges. If you were to look at an anti-atom made of antiprotons and positrons, it would look and behave almost exactly like a normal atom. You could theoretically build stars, planets, and even people out of antimatter. But these two worlds can never touch. When a normal atom and an anti-atom collide, they do not bounce off each other. They do not bond chemically. The opposing charges pull them together with catastrophic force. The positron seeks the electron, the antiproton seeks the proton. When they make contact, the result is total, instant destruction. This is annihilation. It is the most efficient release of energy in the universe. In a nuclear bomb, only a tiny fraction of the mass is converted into energy, less than 1%. In matter-antimatter annihilation, the conversion is 100%. The entire mass of both particles vanishes, transformed instantly into pure energy according to Einstein's equation, E equals mc squared. Typically, when an electron annihilates a positron, they disappear in a flash of gamma rays. Two high-energy photons shoot out in opposite directions, carrying away the energy that used to be mass. The solid, tangible particles are gone. There is no ash, no debris, no leftover structure, just a burst of light speeding away at the cosmic limit. This raises a final, haunting question. If matter can be converted entirely into light, and light can be converted back into matter, as we see in particle accelerators, then what is matter, really? Is it just light that has slowed down and trapped itself in a knot? Is the physical world we touch merely a condensed form of energy, waiting to be released back into the void? In the annihilation event, the atom finds its most dramatic end. It does not decay into something else. It does not leave behind a corpse. It simply stops being stuff and becomes pure radiation. It returns to the energy field from which it was born billions of years ago. Yet, even here, the conservation laws hold. The energy of the gamma rays is exactly equal to the mass of the destroyed particles. The total amount of energy in the universe has not changed by a single joule. The form is lost, but the substance remains. This cycle of creation and destruction, of matter condensing from energy and dissolving back into it, is the heartbeat of the cosmos. From the virtual particles bubbling in the vacuum, to the entanglement connecting distant stars, to the final flash of annihilation, the story of the atom is not a story of permanence. It is a story of flow. Nothing stays. Nothing is wasted. Everything is just passing through on its way to becoming something else. Although electrons and positrons are incredibly small points of mass that are almost negligible on the human scale, the energy released when they annihilate is disproportionately immense. This is because, as Einstein revealed, mass is extremely concentrated energy. Even a speck of matter contains a vast reservoir of power. This is what makes matter-antimatter annihilation so potent and so intellectually captivating. It is the most efficient engine in the cosmos. But the story gets more complicated when we move beyond simple particles to complex structures. If an entire atom meets an entire anti-atom, say, a hydrogen atom colliding with an anti-hydrogen atom, the destruction is a multi-stage catastrophe. First, the outer shells interact. The electron and the positron, orbiting their respective nuclei, are drawn together by electrostatic attraction. They spiral inward and annihilate, flashing into gamma rays. The protective clouds are gone. Now, the naked nuclei face each other. The proton and the antiproton collide. Unlike the clean annihilation of electrons, this collision is messy. Protons are composite particles made of quarks held together by gluons. When a proton and an antiproton smash together, they do not just vanish into light, they shatter into a shower of unstable, high-energy fragments called pions. These pions fly outward, carrying the kinetic energy of the destroyed mass. They exist for only a fraction of a second before decaying into muons, neutrinos, and gamma rays. The result is not a single flash, but a chaotic firework display of subatomic debris. Neutrons and antineutrons behave similarly, adding to the storm of particles. These fragments quickly decay or speed off into the void, carrying away the energy that, moments ago, existed as structured, stable matter. One of the most remarkable aspects of this process is its totality. In a normal collision like a car crash or even a nuclear fusion reaction, something physical always remains. There are twisted fenders, or new helium atoms, or at least ash. But in annihilation, the original identity of the matter is completely erased. It is a clean exchange. Structure becomes radiation. Mass becomes motion. The complex information that defined the atom, its atomic number, its chemical properties, is dissolved into the universal currency of energy. This event is not theoretical fiction. It has been observed countless times in laboratories, particularly in particle accelerators like those at CERN. Here, scientists manufacture antiparticles and guide them into collisions with normal matter to study the debris. We even use this principle in medicine. In a PET scan, a patient is injected with a tracer that emits positrons. Inside the body, these positrons travel only a few millimeters before finding an electron. They annihilate, emitting 2 gamma rays in opposite directions. The scanner detects these rays and works backward to build a precise image of the body's internal chemistry. It is a strange thought. We use the violent death of antimatter to save human lives. Despite how well we understand this process, antimatter presents one of the biggest unsolved mysteries in physics. Where is it? According to our best models of the Big Bang, the universe began as a burst of pure energy. As this energy cooled, it condensed into matter. But the laws of physics are symmetrical. For every particle of matter created, a particle of antimatter should have been created too. The infant universe should have been a perfect 50-50 mix. If that were true, none of us would be here. The matter and antimatter would have annihilated each other immediately, leaving nothing but a universe filled with light. Obviously, that didn't happen. We are here. Galaxies exist. Stars exist. This implies that in the first moments of creation, something broke the symmetry. An unknown mechanism favored matter. The imbalance was incredibly slight, perhaps just 1 extra particle of matter for every billion pairs. But when the great annihilation finished, that tiny 1/billionth of a remnant is what remained. It became everything we see: the stars, the planets, the nebulas, and life itself are made of the leftovers of a cosmic war between matter and antimatter. Why this imbalance occurred is still unknown, and finding the answer is one of the holy grails of modern cosmology. Another open question is gravity. Does antimatter fall down? In theory, according to Einstein's general relativity, gravity couples to mass, not charge. So, an anti-apple should fall to the earth just like a real apple. But scientists are rigorous. They don't trust assumptions. Experiments at CERN, such as the Alpha G experiment, are currently trapping anti-hydrogen atoms and releasing them to see if they drop or however unlikely float up. If antimatter responds differently to gravity, it would overturn our understanding of the universe. So far, early data suggests it falls normally, but the precision is still being refined. Because annihilation follows the strict laws of conservation, the energy release depends on the speed of the collision. In space, if clouds of matter and antimatter met gently, the energy would be purely from their mass. But in a particle accelerator, atoms are pushed to nearly the speed of light. When they collide, the kinetic energy is added to the mass energy. This creates a collision far more powerful than the sum of its parts, allowing heavier, more exotic particles to be born from the impact. Cosmologists have searched the sky for signs of naturally occurring antimatter regions. If there were a galaxy made of antimatter colliding with a galaxy of matter, the boundary between them would be blazing with specific gamma-ray signatures. We have never seen such a boundary. This suggests that if large pockets of antimatter exist, they are so far away that their light has not reached us, or the observable universe is indeed entirely dominated by matter. However, nature can still create antimatter in extreme kitchens. Around black holes and neutron stars, the environment is so energetic that photons can spontaneously split into electron-positron pairs. These particles usually find each other and annihilate almost instantly, contributing to the high-energy glow we detect from these violent objects. The annihilation of atoms serves as the ultimate reminder of the unity between matter and energy. It shows that physical structures, no matter how solid they feel, are temporary arrangements. They can be built up by forces, and they can be unbuilt, returning to the primordial light from which they came. But how do we study these fleeting, violent, or incredibly slow deaths without waiting billions of years or building a collider in our backyard? We turn to the digital realm, simulating atomic demise. With the explosion of modern computing power, scientists can now create virtual laboratories. In these digital spaces, they can simulate the decay of an atom, particle by particle, force by force. This approach allows researchers to explore scenarios that are too dangerous, too rare, or too fast to observe in the physical world. At the core of these simulations are mathematical models derived from the laws of quantum chromodynamics and electroweak theory. These models are instructions that tell the computer how protons repel each other, how the strong force snaps them back, and how the weak force mediates decay. By feeding these rules into a supercomputer, researchers create a digital atom. One major advantage of this approach is control over time. In the real world, the decay of an unstable isotope like polonium-212 happens in nanoseconds, a blink too fast for most cameras. In a simulation, we can stretch that nanosecond into an hour. We can watch, frame by frame, as the nucleus wobbles, distorts, and finally ejects an alpha particle. We can see the transfer of energy, the recoil of the nucleus, and the perturbation of the electron cloud. Conversely, for isotopes like uranium-238, which take billions of years to decay, a simulation can fast forward time, showing the entire decay chain in seconds. We can track the lineage of the atom as it sheds particles, transforming from uranium to thorium to radium, and eventually settling as stable lead. This predictive power is vital for storing nuclear waste. We need to know what a canister of spent fuel will look like in 10,000 years. Building these simulations is a monumental task. The equations of quantum mechanics are probabilistic. You cannot just calculate what will happen. You must calculate all the things that might happen and their likelihoods. This requires a technique called Monte Carlo simulation, where the computer runs the same scenario millions of times, rolling the digital dice differently each time to build a statistical map of reality. This requires high-performance computing clusters of thousands of processors working in unison. These supercomputers crunch the numbers for weeks, to simulate a single complex event. But the output is worth it. The data is often more granular than any physical sensor could provide. Visualization tools then turn these mountains of data into understandable images. We can see 3D renderings of the probability clouds of electrons, or the liquid drop model of a nucleus vibrating before fission. These visuals help physicists spot patterns that are invisible in the raw numbers. For instance, they might notice a specific wobble in the nucleus that always precedes a certain type of decay, giving experimentalists a new signature to look for in the lab. Machine learning is also joining the fight. AI algorithms can sift through the data of billions of simulated collisions to find anomalies, rare events that standard code might miss. They can predict decay rates based on the shape of the nucleus, finding connections that human intuition might take decades to uncover. Simulations also allow us to break physics. We can run a model where the strong force is slightly weaker, or where the mass of the proton is slightly heavier, just to see what would happen. These what-if scenarios help us understand why our universe is tuned the way it is. If the rules were slightly different, would atoms exist at all? Would stars burn? However, a simulation is only as good as the physics we program into it. If our understanding of the laws is incomplete, the model will be wrong. That is why simulation and experiment must walk hand in hand. The simulation makes a prediction. The experiment tests it. If they disagree, that is where the excitement begins. This brings us to anomalous decay, when atoms defy our expectations. Most of the time, atoms follow the rules. We have mapped the decay chains of thousands of isotopes. We know their half-lives, their decay modes, and their energy outputs. But every so often, nature throws a curveball. A particle appears where it shouldn't. A decay happens too fast. An energy signal spikes at the wrong frequency. In 2016, a laboratory in Hungary reported a strange anomaly. They were studying the decay of an excited form of beryllium-8. Standard physics predicted that as the nucleus relaxed, it would emit pairs of electrons and positrons at predictable angles. But the data showed a bump, an excess of pairs, emitted at a specific wide angle. At first, it looked like experimental noise, but it persisted. This signal, now known as the X17 anomaly, has led to a bold hypothesis: the existence of a new, unknown particle, roughly 34 times heavier than an electron. Some theorists suggest this particle could be the carrier of a fifth force of nature, a protophobic force that acts over tiny distances. If X17 is real, it would rewrite the textbooks. Other labs are currently racing to reproduce this result to see if it is a breakthrough or a mistake. Other anomalies appear in exotic isotopes, atoms that are forced to have too many protons or too many neutrons. These atoms live on the edge of stability, the so-called drip line. Here, the nucleus is so unbalanced that it behaves in bizarre ways. For example, scientists have observed two-proton decay. In this rare event, a proton-rich nucleus doesn't just spit out one proton, it ejects two simultaneously. This is not a sequence one then the other, but a coordinated quantum mechanical pairing. The two protons leave together, entangled, like a pair of divers jumping in sync. This phenomenon was predicted decades ago, but only recently confirmed, offering a new window into the pairing forces inside the nucleus. Then there is the mystery of the neutrino. Neutrinos are ghostly particles that barely interact with matter. In standard beta decay, a neutron turns into a proton, an electron, and an antineutrino. This balances the books, but there is a theoretical process called neutrinoless double beta decay. In this scenario, 2 neutrons in a nucleus would turn into 2 protons and 2 electrons, but crucially, 0 neutrinos. This would imply that the 2 neutrinos that should have been created annihilated each other before leaving the nucleus. For this to happen, the neutrino would have to be its own antiparticle, a Majorana particle. If this decay is observed, it would prove that matter can be created without balancing antimatter. It could be the key to explaining why the universe is made of matter at all, solving the mystery of the Big Bang imbalance we discussed earlier. Experiments are currently running deep underground, shielded from cosmic rays, waiting for this single, incredibly rare atomic twitch. It hasn't been seen yet, but if it is, it will change everything. According to the standard model of physics, this shouldn't happen unless the neutrino possesses a unique, almost magical property. It must be its own antiparticle. If neutrinoless double beta decay is ever confirmed, it would be a discovery of monumental proportions. It would hint at entirely new laws of physics and potentially solve the cosmic riddle of why our universe is made of matter rather than antimatter. But the mysteries of decay are not limited to missing neutrinos. There are cases where atoms seem to defy the clock, resisting decay longer than our equations predict. In laboratories that store radioactive materials for long-term study, scientists occasionally encounter samples that refuse to die on schedule. These discrepancies are often minute, a fraction of a percentage point, but in precision physics, even a small deviation is a scream for attention. Are environmental factors quietly playing a role? Is the decay being influenced by external electromagnetic fields or subtle quantum effects we have failed to account for? Or is there an unknown interaction occurring deep inside the nucleus? In high-energy collision experiments, detectors have sometimes picked up electrons or positrons that veer off the expected paths. In other instances, a decay event produces gamma rays with an energy signature that feels off, as if an unseen entity has stolen a portion of the energy. Perhaps most strangely, some experiments suggest that decay processes can appear to pause for infinitesimal moments before resuming. These pauses, too short to measure with a stopwatch but predicted by quantum theory as quantum Zeno effects, suggest that the act of observation itself might stabilize an unstable system. While these pauses do not stop decay permanently, they hint that the process is not a smooth, continuous slide, but a stuttering, probabilistic journey. The search for answers begins with data oceans of it. Particle detectors at facilities like CERN or Fermilab collect readings from trillions of decay events. Researchers sift through this noise, looking for the bump in the graph, a slight excess here, an unexpected drop there. These are the whispers of new physics. While many of these anomalies turn out to be statistical ghosts or loose cables, others stubbornly refuse to vanish. When an anomaly persists, the physics community mobilizes. Investigating anomalous decay requires a rigorous choreography of calibration, repetition, and cross-checking between rival labs. Scientists use both raw experimental data and advanced computer simulations to isolate the cause. If no known pathway explains the weirdness, they begin to whisper about new theories: supersymmetry, where every particle has a hidden partner, or extra dimensions, where gravity might leak away, taking energy with it. Some even speculate that these anomalies are fossilized traces of forces from the dawn of the universe. Whether these bold ideas prove true or not, the very existence of anomalous decay proves that the book of atomic physics is not yet closed. But nature does not just hide secrets in the timing of decay. It hides them in the very structure of matter. This brings us to the realm of hyperexotic atoms. Hyperexotic atoms exist at the ragged edge of possibility. They are Frankenstein creatures of the atomic world, assembled under extreme conditions and surviving for mere flashes of time. Yet, in their brief lives, they act as stress tests for the laws of nature. One way to build an exotic atom is to perform a parts swap. Imagine taking a normal hydrogen atom, one proton, one electron, and replacing the electron with a muon. A muon is a heavier cousin of the electron. It carries the same negative charge, but is 200 times more massive. Because of this extra weight, the muon orbits much closer to the nucleus. In a muonic atom, the electron cloud is pulled in so tight that it actually spends time inside the nucleus itself. This allows physicists to probe the internal texture of the proton with unprecedented intimacy. Even stranger is positronium. This is an atom made not of proton and electron, but of an electron and its antimatter twin, the positron. They orbit each other in a death spiral. In a sense, positronium is an atom with no nucleus at all. It is incredibly unstable, lasting less than a microsecond before the two particles collide and annihilate into gamma rays. Yet, during that tiny lifespan, it behaves like a real atom. It has energy levels, it can form chemical bonds, and it even emits light. Then there are the super heavy elements. These are the giants of the periodic table, forged by smashing lighter elements together in particle accelerators. Elements like oganesson, element 118, are so massive that their electrons move at speeds close to the speed of light, causing relativistic effects that warp their chemical behavior. Most of these giants fall apart in milliseconds. However, nuclear theory predicts an island of stability. The idea is that there are magic numbers of protons and neutrons that create exceptionally robust shells within the nucleus. If we could build an atom with exactly the right combination, perhaps 114 protons and 184 neutrons, it might not decay instantly. It might last for minutes, days, or even millions of years. Finding this island is like searching for a solid rock in a turbulent ocean of instability. So far, we have only seen hints, atoms that survive just a little longer than they should, but the shore remains out of reach. Some exotic atoms are even weirder, involving strange quarks. Normal protons and neutrons are made of up and down quarks, but in high-energy collisions, we can create baryons containing strange quarks. If one of these particles gets captured by a nucleus, it forms a hypernucleus. These hypernuclei do not exist naturally on Earth, but they might be common in the crushed cores of neutron stars. Studying them here gives us a peek into the hearts of the densest objects in the cosmos. Beyond matter, we even try to bottle antimatter. Creating antihydrogen is hard. Keeping it is harder. Since antimatter annihilates upon touching any normal container, scientists use magnetic traps to suspend these anti-atoms in a vacuum. For minutes at a time, we can hold a piece of the mirror universe in a bottle, blasting it with lasers to see if it behaves exactly like our own. Then there are the theoretical ghosts, magnetic monopoles, particles with only one magnetic pole, or atoms bound with dark matter. These remain in the realm of speculation, but they drive the experiments that push the boundaries of what matter can be. This entire pursuit, tracking anomalies, building exotic atoms, leads to a profound philosophical crisis in physics: the conservation of information. Imagine watching an unstable atom decay. We measure the energy, the mass, the speed of the debris, but the atom before the decay held more than just numbers. It had a unique quantum state, a specific history of how it was formed, its spin, its entanglement. When it decays, that specific arrangement is broken. Does the information that described it vanish? According to the bedrock principles of quantum mechanics, the answer must be no. The evolution of the universe is supposed to be reversible. If you had a perfect computer and could track every single photon and particle from a decay event, you should theoretically be able to run the simulation backward and reconstruct the original atom. Information, like energy, is never lost. It is merely scrambled. However, this belief clashes violently with the reality of black holes. When matter falls into a black hole, it is crushed out of existence. If the black hole later evaporates via Hawking radiation, what happens to the information of the atoms that fell in? If it is destroyed, then quantum mechanics is broken. If it survives, where is it? This black hole information paradox forces physicists to rethink what memory means in the universe. Some suggest that information is smeared across the event horizon like a hologram. Others believe it is encoded in subtle correlations within the radiation, hidden in the quantum noise. This debate has implications for atomic decay right here on Earth. When an atom decays, its information is scattered into the environment, becoming entangled with the air molecules, the detector walls, and the photons leaving the room. It becomes practically impossible to retrieve, but in principle, it is still there. The universe remembers everything. It suggests that the vacuum of space itself might act as a repository. When a particle passes through or decays, its gravitational and quantum influence might alter the structure of space-time just enough to leave a record, not like a written note, but like a footprint in soft soil that fades but never truly disappears. If this is true, then death, whether atomic or biological, is not an erasure, it is a redistribution. The data of existence is conserved, woven into the ever-expanding tapestry of the cosmos. So, where do we go from here? What is the future of our relationship with the dying atom? The frontier lies in precision and control. In laboratories around the world, scientists are building atomic traps, using lasers to cool atoms to temperatures just a whisper above absolute zero. In this ultra-cold stillness, the jittery motion of the atomic world slows down. Here, we can watch the breath of an atom before it decays. We can measure transitions with such accuracy that they act as clocks, ticking out the rhythm of the universe. New detectors are coming online, buried deep underground in mines to shield them from cosmic rays. They are waiting for the rarest events in nature, like the neutrinoless double beta decay that might happen only once in a trillion years. Capturing just one of these signals would be like hearing a whisper in a hurricane, but it would change everything we know about matter. Quantum computing promises to be the ultimate tool. Instead of just observing atoms, we will use them to simulate themselves. A quantum computer could model the decay of a hypernucleus with a level of detail that no classical supercomputer could touch. It might allow us to test drive new laws of physics in a virtual sandbox. Looking further ahead, could we one day control decay? Could we stabilize radioactive waste by forcing it to decay faster? Could we use targeted atomic decay for nanomedicine, delivering energy to a single cancer cell while leaving the rest of the body untouched? These are not just dreams. They are the logical next steps in a journey that began when we first realized that the world is made of parts. We have gone from thinking atoms were eternal, to watching them die, to realizing that their death is the creative engine of the universe. The atom does not just end, it transforms, it radiates, it remembers, and in doing so, it tells the story of everything that was and everything that will be. But what if we could intervene? What if the ticking clock inside an unstable atom could be paused, reset, or rewritten? These questions, once the domain of science fiction, are now moving into the realm of experimental physics. The first step in this revolution is teaching machines to see what we cannot. Artificial intelligence does not suffer from human bias. It does not need to know what it is looking for to find something interesting. In the flood of data from particle colliders, AI algorithms can simply flag outliers, patterns of decay that deviate from the standard model by a fraction of a percent. If this approach matures, it might reveal subtle mechanisms of stability that human researchers have overlooked for decades. It could lead us to the holy grail of nuclear physics, engineering immortality in matter. We have already begun this journey by creating synthetic atoms. Elements like oganesson, element 118, and flerovium, element 114, do not exist naturally on Earth. They are born in the violence of particle accelerators. Each new element adds a line of code to our understanding of the atomic software. But more importantly, these artificial creations prove that atomic structure is not fixed. It is flexible. It can be extended, altered, and built from scratch. This raises a provocative question. Could we design an atom that never decays? In nature, we already have models of near immortality. Hydrogen, helium, carbon-1, 2. These atoms hold together for billions of years, effectively eternal on human timescales. Scientists study these survivors to understand the secret of their resilience. Is it the symmetry of their nucleus? The precise balance of binding energy? Once we crack the code of natural stability, the next logical step is to replicate it and then improve upon it. However, the real challenge is not just building a stable core. It is controlling the chaos that surrounds it. Atoms decay when they reach a tipping point of imbalance. A neutron slips its bonds, or a surge of energy fractures the nucleus. But what if we could build a cage? What if we could construct an external field, a shield that physically prevents the atom from falling apart? This concept drives current research into atomic traps and quantum xenodynamics. These setups use lasers and electromagnetic fields to suspend atoms in a vacuum, freezing their motion to near absolute zero. In these suspended states, we have observed that the rate of decay can be subtly manipulated. By observing the atom constantly bombarding it with measurements, we can, in theory, reset its quantum clock, delaying the inevitable. While we cannot yet stop decay entirely, we are learning to slow it down. We are moving from observing death to guiding life. Another frontier is atomic repair. In biology, living cells have enzymes that patch damaged DNA. Could we develop a similar mechanism for matter? If a nucleus loses a neutron, could we inject another to restore balance? If a heavy atom begins to wobble, could we use a pulse of energy to stabilize it before it fissures? Techniques like neutron capture already allow us to transform one element into another inside reactors. Extending this into a precision tool for healing atoms is a distant dream, but it is no longer scientifically impossible. The rise of quantum computing and nanotechnology is laying the groundwork for this future. To build a quantum computer, we need absolute control over individual atoms, trapping them, reading their states, and shielding them from the noise of the outside world. As these tools become sharper, we may reach a point where atomic engineering becomes a standard discipline. Imagine a future of synthetic atoms. These would not be mere novelties in a lab. They would be tools, We could design atoms that are immune to radiation, or atoms that store immense amounts of energy without the risk of meltdown. We could build construction materials that do not degrade over millennia, or medical tracers that turn on and off on command. But this power comes with risks. In nature, decay is a necessary part of the cycle. It recycles matter, heats the core of our planet, and drives the evolution of stars. If we fill the world with matter that refuses to break down, we disrupt that cycle. Immortal matter would be a pollutant unlike any other stuff that the universe cannot digest. Perhaps these designer atoms will remain specialized tools used only for the hull of a starship or the memory core of an archive, while the rest of the world continues to live and die by natural laws. Ultimately, the goal is not to force the atom to live forever, but to master the art of transformation. We want matter that is responsive. We want atoms that adapt, evolve, and change state at our will. We are moving toward a future where matter is not just stuff, but programmable hardware. But to truly test the limits of what matter can endure, we need a testing ground more extreme than any laser trap. We need the ultimate crusher, the black hole. We cannot fly to a black hole, so we are trying to build them, or at least their ghosts, right here on Earth. This is the search for artificial black holes. These are not the star eaters of science fiction. We are talking about analog black holes, controlled simulations created in the lab using fluids, sound waves, or light. The goal is to create a horizon, a point of no return, where the flow of the medium, like water or light, moves faster than the waves can travel against it. By sending sound waves into a supersonic fluid flow, scientists have created sonic black holes. Sound waves that get too close to the drain are trapped. They can never swim back upstream. Mathematically, the equations governing these sound waves are identical to the equations governing light near a real black hole. Why do this? Because it allows us to study atomic death in a warped reality. In these analogs, we can watch how waves representing particles are stretched and torn apart near the horizon. We can look for Hawking radiation, the faint energy that Stephen Hawking predicted should leak from black holes. In 2019, researchers using a Bose-Einstein condensate, a super-cold state of matter, reported seeing thermal radiation emitting from their artificial horizon. This suggests that even in a vacuum, destruction creates something new. If we could generate a true micro-black hole in a particle collider, a theoretical possibility if gravity behaves differently at small scales, it would be the ultimate stress test. We could throw a single atom into it and watch it disintegrate. Does it rip apart into quarks? Does it dissolve into pure geometry? Or does it emerge, scrambled but conserved, in the Hawking radiation? These experiments are testing the boundary between quantum mechanics, the rules of the small, and general relativity, the rules of gravity. Currently, these two rulebooks do not agree. Seeing how an atom dies at the edge of a black hole might be the key to uniting them into a theory of everything. It also opens up the strange possibility that black holes are not just destroyers, but factories. Theoretical physics suggests that the extreme energy density near a horizon could spark the creation of new particles from the vacuum. An atom might be torn apart, but its energy could be instantly reassembled into new, exotic forms of matter that do not exist anywhere else. Destruction and creation happening in the same breath. But why stop at our universe? Modern cosmology forces us to consider an even wider stage, the multiverse. The theory of the multiverse suggests that our universe, with its specific gravity, electromagnetism, and nuclear forces is just one bubble in a cosmic foam. In other bubbles, the settings might be different. This means the story of the atom could have infinite endings. Imagine a universe where the strong nuclear force is slightly weaker. In such a place, protons and neutrons could not stick together. Nuclei would never form. Hydrogen would be the only element forever drifting in a sterile dark. There would be no fusion, no stars, no carbon, no life. Atomic death would be instant and universal. Matter would crumble as soon as it tried to build itself. Conversely, imagine a universe where the strong force is dialed up. Atoms would bind together with ferocious strength. Fusion would be so efficient that stars would burn through their fuel in days, exploding violently. Or perhaps, nuclei would be so stable that radioactive decay never happens. The universe would be filled with monstrously heavy, frozen elements, statues of matter that never change, never evolve, never release their energy. A dead, static world. Or consider a universe with different spatial dimensions. In our 3D world, forces like gravity and electromagnetism weaken as they spread out, following the inverse square law. This balance allows electrons to orbit nuclei stably. In a 4D or 5D universe, the math changes. Orbits might become unstable. An electron might spiral into the nucleus instantly, or fly off into the void. Atoms, as stable structures, might be geometrically impossible. These counterfactual universes teach us something profound about our own home. We exist on a knife edge of stability. Our atoms are durable enough to build mountains and memories, yet fragile enough to fuel the sun and evolve. Atomic death is tuned to exactly the right frequency. It is not a flaw in the design. It is the feature that makes complexity possible. So, where does this leave us? We started this journey asking, where do atoms go when they die? We learn that they do not vanish. They transform. They break down in the quiet statistical roulette of radioactive decay. They are crushed and reborn in the fiery forges of stars. They are ripped apart and scrambled at the edge of black holes. They are converted into pure light in the flash of annihilation. The atom is not a permanent object. It is a temporary pattern, a knot tied in the energy fields of the universe. When the knot unties, the string remains. The energy that makes up your body right now has been part of 1 trillion other stories. It was there at the Big Bang. It was cooked in the heart of a dying star. It drifted through the cold void for aeons before assembling into you. And when your biological time ends, that energy will continue. Your atoms will scatter. Some will become part of the earth. Some will become air. Some may eventually escape the planet to be part of a new star. The information of your existence, the quantum signature of your being, is woven into the fabric of the cosmos, conserved forever in the great ledger of physics. In the quantum world, there is no final silence. There is only the constant, shimmering dance of transformation. The atom dies, but the universe lives on, carrying the memory of everything it has ever been. In our universe, the laws of physics seem set in stone. But what if we lived in a reality where the geometry of space was fundamentally different? If a universe had 4 or more spatial dimensions, the architecture of the atom would collapse. Electrons might not find stable orbits. Instead, they could spiral inward or drift away entirely. The gravitational force, which weakens with distance, would drop off much faster in higher dimensions. This could make planetary systems impossible and atomic structures fleeting. Decay in such a world might not be a slow, probabilistic decline, but an instant unraveling as forces stretch too thin across the extra space. Even stranger is the possibility of a universe where time flows differently. Our physics is built on a linear arrow of time, cause precedes effect, but theoretical models allow for universes where time is cyclical, nonlinear, or even bidirectional. If atoms existed in such a place, their decay might not be a one-way journey into oblivion. Instead of dissolving permanently, an atom might disintegrate and then reassemble, like a movie played in reverse. In this world, destruction is not an endpoint. It is merely one half of a breathing cycle. The same particles would come apart and come back together in an endless, rhythmic loop. In more speculative corners of the multiverse theory, there might be regions where quantum mechanics does not rule. Imagine a deterministic universe where every outcome is fixed, with no room for probability or chance. In such a place, the concept of half-life, which relies on the randomness of decay, would be meaningless. Atoms would either be eternal or they would vanish at a preordained moment, ticking down like clockwork bombs. Some researchers even entertain the idea of baby universes, small, newly formed regions of space-time that bud off from a parent universe. It is hypothesized that extremely high-energy events, like the collapse of a massive black hole or a specific type of atomic instability, could trigger these births. In this view, the death of an atom in our universe could be the Big Bang of another. Atomic demise would not be a loss, but a seed, planting new realities with their own unique physics. From a research standpoint, exploring these questions is nearly impossible with current technology. We cannot step outside our bubble to check the neighbors. However, theoretical physicists can visit these worlds using mathematics. They run simulations where they tweak the fundamental constants of nature, turning up the strength of gravity, dialing down the weak nuclear force to see what happens. These parameter sweeps reveal that our universe is in a life-friendly zone. If the strong force were just a few percent weaker, deuterium would not form and stars would not shine. If it were a few percent stronger, hydrogen would burn up almost instantly. The identity of the atom, therefore, is not fixed. It is conditional. Its life, its stability, and its death are bound to the specific laws of its home universe. Change the laws, and you change the definition of death. But even within our own universe, there is a question that haunts physicists. Does the universe remember? Atoms are not just billiard balls bouncing in the dark. They exist in defined quantum states, specific energy levels, spin directions, and momentum vectors. When an atom decays, it transitions from one state to another. The particles it ejects, the alpha, beta, and gamma radiation, carry precise amounts of energy and momentum. They are not random debris, they are a coded message. This concept is known as path dependence. A system is defined not just by what it is now, but by how it got there. The daughter atom remembers the parent in its configuration. The photon emitted by an excited electron carries the fingerprint of the orbital it jumped from. In this sense, the history of the atom is written into the structure of the universe around it. Quantum entanglement makes this memory explicit. If two particles are entangled and one decays, the information is not lost. It is transferred to the partner. It is preserved in the correlations between them. This isn't memory like a computer hard drive, but it is a quantum record, a trace that persists. However, over time, this information tends to scramble. This is the process of decoherence. The delicate quantum states leak into the environment, becoming entangled with the air, the walls, and the radiation field. The clear, sharp note of the atom fades into the noise of the room. But technically, the information is still there. It is just hidden, scattered across trillions of interactions. This raises a profound possibility, reconstructability. In principle, though, certainly not in practice, if you could measure every particle and field in the universe with infinite precision, and you knew every law of physics perfectly, you could rewind the tape, you could trace the scattered noise back to the source, and reconstruct the atom that died 1 billion years ago. If this is true, then atoms never truly forget. Even after destruction, they leave a mark that says, "I was here." But what happens when the universe itself grows too old to remember? Let us teleport to the very end of the line, the era of heat death. Imagine waking up in a place where nothing moves, nothing shines, and nothing grows. Every star has burned out. Every black hole has evaporated. Every atom that could decay has decayed. This is not just the end of a world. It is the end of change. At first glance, there is only darkness, not the textured darkness of a night sky, but a flat, absolute void. The temperature is barely distinguishable from absolute zero. There is no sound, for there is no medium to carry it. Long ago, the universe was filled with the violence of creation, galaxies colliding, supernovas exploding. But in the wake of heat death, those days are a forgotten dream. The forces that held matter together have finally unraveled. Protons, if they are unstable as some theories suggest, have decayed into leptons and photons. Neutrons are long gone. Electrons drift through the void, separated from one another by light years, with no nuclei to orbit. What remains is a photon gas, a thin mist of radiation that has been stretched by the expansion of space until it has almost no energy left. This is the state of maximum entropy. The universe has used up its potential. All the gradients, hot to cold, high pressure to low pressure, have leveled out. Without a difference in energy, no work can be done. No life can think. No clock can tick. Time still exists, technically, but it has lost its meaning. In our era, we measure time by events, a heart beating, a planet orbiting, an atom decaying. But in a universe where nothing happens, one moment is identical to the next. Time becomes an empty dimension, a road with no milestones. Gravity is still a law, but there is nothing left to bend. The massive structures that once warped space-time have dissolved. The ripples of gravitational waves have faded into a flat, silent hum. It is a lonely picture, but there is a strange serenity to it. The universe began in a hot, dense flash of chaos. It spent billions of years building complexity atoms, stars, galaxies, minds. It raged and burned and evolved. And now, at the end of the trillionth eon, it rests. Every atom that ever existed, every struggle, every burst of light was part of a trajectory that led to this moment of perfect stillness. If we ask what happens after heat death, the scientific answer is nothing. That is the point. There are no new beginnings in this model, no phoenix rising from the ashes, just an endless, peaceful drift, unless, of course, the vacuum is not truly empty. Some speculative theories suggest that even in this ultimate winter, quantum fluctuations could randomly spark a new Big Bang, resetting the clock. But until we know for sure, heat death remains the final punctuation mark of existence. We have followed the atom from its birth in the early universe, through its violent life in the stars, its invisible dance of decay, and finally to its dissolution at the end of time. It is a story of transformation. The atom is not a permanent thing. It is a temporary arrangement of energy, borrowed from the vacuum and eventually returned to it.